125 light-years away from Earth, a planet orbits a star shrouded in mystery. K2-18b, a world unlike any other in our solar system, could hold the keys to answering the age-old question, are we alone in this vast cosmos? Very recent discoveries by the James Webb Space Telescope hint at something extraordinary, something that could change our understanding of life itself. But there's more to this story than meets the eye. We'll talk about this in detail in a bit, but before that, we'll discuss briefly what exoplanets are and how astronomers detect them. So, stay with me, because we're about to embark on this exciting journey together to uncover what might just be the first step in finding life beyond Earth. Welcome to Astrobits Daily, and you're watching another episode of Astrobits Deep Dive. If you're new to the channel, please consider subscribing for exciting content about the universe. Look up at the clear night sky. What do you see? Thousands of stars twinkle back at you. Each one is a distant sun, a burning ball of gas light years away. Imagine the worlds that might orbit those stars. Could some of them harbor life? For centuries, humans have gazed at the stars and pondered this question. Are we alone in the universe? The search for extraterrestrial life, particularly on planets outside our solar system, has become one of the most exciting endeavors in modern science. As we explore the cosmos, we are driven by a fundamental human desire to understand our place in the grand scheme of things. Exploring exoplanets is not just about finding extraterrestrial life. It is about understanding the nature of life itself. Our sun is just one among 100 billion stars in the Milky Way galaxy, just like the Milky Way galaxy is one among a trillion other galaxies scattered across the vast universe. We now know for a fact that other stars have planetary systems too. Planets that orbit stars beyond our sun are called exoplanets. These distant worlds come in a stunning variety of sizes, compositions, and orbital characteristics. Some are gas giants larger than Jupiter, while others are rocky planets like Earth. Some orbit their stars closely, completing an orbit in just a few days, while others take centuries to make one journey around their host star. The discovery of exoplanets has revolutionized our understanding of planetary systems. It has shown us that our solar system, while special to us, is just one of many possible configurations. The sheer diversity of exoplanets has fueled our imagination and spurred us to develop new technologies to find and study these distant worlds. We'll get to K2-18b in just a moment. Before that, let's find out how astronomers use very clever techniques to find exoplanets like K2-18b from such great distance. Finding exoplanets is a challenging task. They are incredibly faint and difficult to see directly, often lost in the glare of their host stars. However, scientists have developed ingenious methods to detect these elusive worlds indirectly. These methods rely on observing the subtle effects that exoplanets have on their host stars. One of the most successful methods is the transit method. This technique looks for tiny dips in a star's brightness caused by an exoplanet passing in front of it. Imagine insects flying in front of a street lamp. The insects themselves are too small to see from a distance, but their passage would cause a momentary dimming of the light. Another powerful method is the radial velocity method, which detects the wobble of a star caused by the gravitational pull of an orbiting exoplanet. Astronomers can detect these subtle wobbles in stars, revealing the presence of unseen planets. The transit method is a powerful tool for discovering exoplanets. It relies on the chance alignment of an exoplanet's orbit with our line of sight from Earth. When an exoplanet passes directly between its host star and Earth, it blocks a tiny fraction of the star's light. This transit creates a small dip in the star's brightness, which can be detected by sensitive telescopes. The amount of light blocked during a transit tells us the size of the exoplanet. A larger planet will block more light than a smaller one. By measuring the time between transits, astronomers can determine the exoplanet's orbital period, which reveals its distance from its star. The transit method is most sensitive to large planets orbiting close to their stars, as these planets produce the most noticeable dips in starlight. However, advancements in telescope technology have enabled the detection of smaller and more distant exoplanets using this method. K2-18b was discovered using the transit method. The radial velocity method, also known as the Doppler spectroscopy method, relies on the gravitational tug-of-war between a star and its orbiting exoplanet. Both the star and the planet orbit their common center of mass. Because the star is much more massive than the planet, it moves in a much smaller orbit. However, this motion is still detectable from Earth. As the star moves towards us, its light is slightly compressed, causing a blue shift in its spectrum. As it moves away from us, its light is stretched, causing a redshift. Astronomers can measure these tiny shifts in the star's spectrum to detect the wobble caused by an orbiting exoplanet. The radial velocity method works best when we're trying to detect massive planets orbiting close to their stars, as these planets produce the largest wobbles in their host stars. This method also provides information about the exoplanet's mass and orbital period. Since K2-18b is also a potentially habitable exoplanet, let's discuss what properties make a planet habitable, and then delve deeper into the exciting findings of JWST. Not all exoplanets are created equal. Some are scorching hot gas giants, while others are frozen wastelands. As you'll discover in a moment, finding rocky planets in the Goldilocks zone with specific atmospheric properties is crucial while discussing about possible extraterrestrial life on these distant worlds. Anyway, the ultimate goal of exoplanet research is to find planets that could potentially support life as we know it. These are known as potentially habitable exoplanets. But what makes a planet habitable? The most important factor is the presence of liquid water, which is essential for all known life. A habitable planet must orbit its star within a specific distance range known as the habitable zone or the Goldilocks zone, where temperatures are suitable for liquid water to exist on the planet's surface. Other factors that contribute to habitability include the planet's atmosphere, its magnetic field, and its geological activity. The atmosphere must be able to protect the surface from harmful radiation and regulate the planet's temperature. A magnetic field can shield the planet from the solar wind, which can strip away its atmosphere over time. Geological activity, such as volcanic eruptions, can help to replenish the atmosphere and provide nutrients for life. We're now addressing the elephant in the room, K2-18b. Though astronomers have made remarkable discoveries in the search for habitable exoplanets, in the recent years, K2-18b is the cream of the crop. K2-18b is a Earth-like exoplanet located about 125 light-years away. This exoplanet orbits within the habitable zone of its host star called K2-18, a red dwarf star much cooler and smaller than our Sun. What makes K2-18b very intriguing is the detection of carbon dioxide, organic compounds like methane, and most recently, dimethyl sulfide in its atmosphere. This recent discovery made using the James Webb Space Telescope is so groundbreaking because on Earth, dimethyl sulfide is only produced by certain living microorganisms like phytoplankton and some algae. Now, before we jump to conclusions, let me clarify. The presence of dimethyl sulfide and methane alone is not conclusive evidence of extraterrestrial life. Detection of such molecules is considered a potential biosignature, but further evidence is usually required to confirm biological activity. So, while this discovery is very exciting, we cannot simply conclude that K2-18b is teeming with life. But this detection makes K2-18b a prime target for more rigorous studies about potential biological activity on this planet. The discovery of K2-18b and other potentially habitable exoplanets has fueled our hopes of finding life beyond Earth. It has shown us that such planets do exist, and it has given us a glimpse of the incredible diversity of worlds that await our exploration. Studying exoplanets helps us find our place in the universe. By studying other planetary systems, we can learn about the processes that led to the formation of our own solar system and the conditions that allowed life to arise on Earth. The search for life beyond Earth forces us to confront fundamental questions about the nature of life itself. What are the essential ingredients for life? How does life arise and evolve? Are there other forms of life out there that are completely different from anything we can imagine? So are we alone in this universe? The discovery of exoplanets, particularly those that lie within the habitable zones of their stars, has brought us closer than ever to answering this fundamental question. While we have yet to find definitive evidence of extraterrestrial life, the search continues. New telescopes and technologies are being developed that will allow us to study exoplanets in even greater detail, searching for biosignatures or chemical fingerprints of life in their atmospheres. When we uncover definitive proof of extraterrestrial life, whether it's a microorganism clinging to a rock on a distant world or an entirely new form of biology, it will be nothing short of a cosmic awakening. This discovery will shatter the narrow confines of our human-centric perspective, forcing us to confront the humbling truth that we are but one small part of a vast, intricate tapestry woven across the universe. We'll cover extraterrestrial life in the lens of Fermi paradox in another deep dive video. If you're still here, thank you. Check out the linked video if you're interested to know more about where our best theory of gravity fails and what Einstein's greatest blunder was. Until next time, stay curious.